right, let's remind ourselves of what we were up to. We're trying to fuse nuclei together, charges Z1e and Z2e, and they have to overcome their mutual Coulomb repulsion, the fact that they're both positively charged. And so we can think calling that E of the incoming nucleus. If we think in terms of like the equivalent one-body problem, you got a fixed potential at the origin and the reduced mass nucleus coming in. You want to think of it like that. You could also think of it as, we'll think of it like that. So the idea is that classically, in order for them to fuse, in order for them to get to where they attract one another via the strong nuclear force that would overcome the Coulomb repulsion, classically you would expect that this wouldn't do the trick because the incoming nucleus's energy isn't enough to top the maximum value of the Coulomb potential. And so we were talking about we were going to make an estimate of what temperature you would need to have the nuclei come in with one another, come into one another. Actually, I'm going to say incoming nuclei here, so I didn't emphasize that this is really the two nuclei. Both their energies are involved here. You would need it to be above the top value of the Coulomb barrier there. And so let's make this estimate. So classically, as we said, I think we said this already. I ended up forgetting too where we were last time. The distance of closest approach R subclassical, we'll call that, is given by, and again on our picture, R classical would be that value of R right there, the classical turnaround point, the point where the incoming kinetic energy turns into potential energy, if you will, to get to the point where the incoming kinetic energy is equal to the potential energy at their closest point of approach, because then they're not moving, and so all their energy is potential energy. Remember that the total energy minus the potential energy is the kinetic energy. So here's the point where the kinetic energy is zero. We would say that 1/2 mu m v squared is equal to Z1, Z2, E squared over 4 pi epsilon naught R classical, because this is saying that initial PE, initial KE, the initial kinetic energy, is equal to the PE at closest approach. Coming in, they've got zero potential energy, it's all kinetic energy. At closest approach, the energy is all potential energy because the kinetic energy has gone to zero, and so that's our condition, so we can figure out what our classical is in terms of V, et cetera, et cetera. So, does this make sense? What questions do you have at this point? So let's see what this buys us then. We want to turn this into a temperature because we know that how fast the particles are moving is related to the temperature. They're not all moving the same speed, but the higher the temperature, the faster on average the particles are moving. And what we can do is, if we're trying to turn this into a temperature, is to say, okay, well, let's set the temperature equal to the thermal, let's set the thermal average RMS, what do I want to say? The thermal RMS kinetic energy equal to 3/2 kT. So if we replace V squared with the thermal RMS value that we got last semester, remember we said that the thermal average kinetic energy per particle, 1/2 mu VRMS squared, that's equal to 3/2 kT. Remember that each degree of freedom gets half kT of average thermal energy for the motion of the particles. They've got 3 degrees of freedom. They're moving in 3 dimensions. And so 1/2 mu VRMS squared, the thermal RMS kinetic energy, is equal to 3/2 kT. So this gives us a relationship between the temperature and the typical speeds of the particles. And we said the strong nuclear force kicks in at about a separation of a femtometer, a Fermi. How big is a femtometer? How big is a Fermi? Same thing. It's about 10 to the minus what meters? Yeah, 10 to the minus 15 meters. So let's say our condition is they need to approach to within 10 to the minus 15 meters of one another, a Fermi of one another, and set and use that our classical be on the order of Fermi femtometer, which is 10 to the minus 15 meters for a typical nucleus. It's a typical nuclear size. We can estimate the temperature required for fusion if the particles behave classically, where they have to overcome the Coulomb barrier. Estimate the temperature required for fusion if the particles behave classically. So we say, keep your grip there. So we say, our classical, okay, solve this expression. So put 3/2 kT over there. Solve this expression for our classical. Our classical equals 2 Z1 Z2 E squared over, and we'll call this like T classical, the temperature expected for classical fusion to occur when we set our classical to a Fermi. Solve for our classical, 2Z1 Z2 E squared over 12 pi epsilon naught k T classical equals 1 Fermi. And then say, okay, well then that, what does that imply for T classical? You get Z1 Z2 E squared over 6 pi epsilon naught k times a Fermi. Plug in the numbers. And if we do that for protons, we'll get a result after I let you catch up. All right. I don't really have to solve for our classical first. I could just put in 1 Fermi here and solve for T classical directly if you like. Now it's going to depend on the nuclei involved, what we would estimate for this. Since we're talking about, say, hydrogen fusion in the sun, it's mostly the proton-proton chain. What's the first step in the proton-proton chain? Two protons make deuterium. So let's just look at the first step there. Two protons come in. What's Z1 and Z2 if it's two protons approaching one another? What's Z1 for the first nucleus? What's Z2 for the second nucleus? If they're both protons, Z1 and Z2 are just one, right? Because it's just a single proton in each nucleus. So for two protons, Z1 equals Z2 equals 1. This yields, put in the numbers, T classical is about, oh, I lied last time, I said a trillion. I was just kidding. About 10 to the 10th Kelvin. Still big. 10 billion Kelvin, roughly speaking. However, models indicate that the actual temperature of the sun's core is about 1.6 times 10 to the 7th Kelvin, about 16 million Kelvin. And so apparently it's more like 16 million Kelvin is enough. In general, calculations show about 10 million Kelvin is the minimum temperature to ignite the proton-proton chain. Well, that's 1,000 times smaller than 10 billion Kelvin. So what gives? What's up with that? Why does the actual temperature that we need be so much lower than what we would estimate classically? How can these particles be fusing if, classically speaking, they could not overcome their electrical repulsion and get close enough to fuse with one another? By the way, when you say what gives here, that must come from German, because German uses the word give, so to speak, to mean is, in the sense of, if you say, es gibt, it gives, that actually means it is in German. It's kind of an idiom. So I suspect we got, have you heard that before? So we say, oh, well, what gives? That, I think, comes from German, essentially. So that's a colloquialism there. So what gives? What's going on here, in other words? What's going on here? We've mentioned it. What's happening? What's saving us, so to speak? Why, it's quantum tunneling, quantum tunneling, quantum tunneling. Yay, quantum tunneling. Quantum tunneling is what gives. So, let's talk about that. We'll have to wave some chicken feet along the way. We're not going to do the full-blown derivation of everything, so you'll have to take my word on a few things. But let me again kind of sketch the potential well for the particles interacting with one another. And down here, really kind of on another copy of the R-axis here, let's write a qualitative picture of like the wave function. Now it really depends, it'd be in 3 dimensions, we'll just call it like psi r here, assuming that it's spherically symmetric so that it doesn't have any angular dependence, although it's good, but that's worrying too much. So let's suppose our incoming particle has this much energy again, well, our incoming particles, I should say. And again, we're really looking at this from the standpoint of the equivalent one-body problem, which you can do in quantum mechanics as well. You can write down the wave function of the reduced mass and look at it from that point of view. So that's really what we're doing here. And so here, is the classical turning point, as close as they could get to one another, classically speaking. And so here is E, here is potential energy U, and in quantum mechanics, if we just pretend that this is a one-dimensional quantum mechanical problem, to keep things simple, what does the one-dimensional Schrodinger equation looks like? You can study quantum mechanics for quantum tunneling in one dimension as well. What is the one-dimensional Schrodinger equation? Do you remember? No, you don't remember the Schrodinger equation. Does anybody remember the Schrodinger equation? Okay, I'll help you. Minus h bar squared over 2m, something, something.
I do remember the H bar.
You do remember the h bar? Congratulations. Minus h bar squared over 2m. What am I putting there?
D squared dt.
Not dt. Got a...
dx dt.
No, it's got the wave function here.
Oh, it's
D squared psi dx squared. So I'm going to pretend this is like a function of x instead of a function of r. Minus h bar squared over 2f d squared psi dx squared. And I'm also writing the time-independent Schrodinger equation here. We're going to leave out the time-dependent. So minus h bar squared over 2m d squared psi dx squared plus what psi equals what psi. This is actually worth memorizing the Schrodinger equation. It's the one-dimensional one particular. Since I'm calling it u instead of v, I'll say plus u psi. You might have also seen plus v psi equals, what's on the other side? Yeah, E, what else? Psi. Minus h bar squared over 2m d squared psi dx squared plus u psi equals E psi. Again, we often see this plus v psi equals E psi. Is the one-dimensional Schrodinger equation. We'll pretend this is a one-dimensional Schrodinger equation problem. And so think of the infinite square well. Everybody's favorite there. In the infinite square well, if we set v equals 0 inside the well, then you just get minus h bar squared over 2m d squared psi dx squared equals E psi by itself, right? If v is 0 inside the well, you get minus h bar squared over 2m d squared psi dx squared is equal to E psi. And so then we do this. We say, okay, d squared psi dx squared is equal to minus 2me over h bar squared psi. And we will then say, well, that by definition is minus k squared psi. So we call all this stuff k squared. And this is saying the second derivative of psi is minus k squared times psi itself. What are the solutions of that equation? If you have the second derivative is minus k squared times the function itself. If I look for real solutions of that, what are the solutions of that equation? This should be knee-jerk. You should know this. Tell me a function whose second derivative is minus k squared times the function itself. There's two of them, and there's two linearly independent real solutions to that equation that are kind of natural choices. So what's a function whose second derivative is minus a constant times itself?
Sine and cosine.
Yeah, sine and cosine. Sine and cosine, right? This looks a lot like the harmonic oscillator equation. There it's just in time instead of in space. The solution of this is a constant times sine kx plus another constant times cosine kx, right? Because if I differentiate sine kx, what do I get? I'm reviewing quantum mechanics here, okay? But I think I need to because none of this is going to make sense to you if you don't remember how the Schrodinger equation works. So if I have psi equals a sine kx, what's d psi dx? Sine differentiates to cosine, so it's not a minus sign yet, right? So this derivative is ka cosine kx, and if I take another derivative, what's the derivative of cosine kx? Minus k sine kx, so you get a minus k multiplied here, so I'm going to get minus k squared k sine kx. Well, what's a sine kx? That's psi itself. And so indeed, a sine kx has the property that its derivative is minus k squared times the psi that you started with. And if you plug in cosine kx, you'll get the same sort of thing because cosine will differentiate to minus sine, and the minus sign differentiates to minus cosine with two factors of k coming in when you take the two derivatives. So any linear combination of a sine kx plus b cosine kx is a solution of the Schrodinger equation inside the well. If you add a sine and a cosine together, it's sinusoidal. It's a sinusoidal function. It'll have phase shift. You can write it as a sine of kx plus a phase shift, or a cosine of kx plus some different phase shift. We mentioned this. So any value of k produces a solution, right? And no matter you can get a solution for any energy whatsoever. Every energy produces a solution, but what picks out some of them as special? This is something we mentioned before in connection with solutions for stellar models. Yes?
They satisfy the boundary conditions?
Has to satisfy the boundary conditions, right? Has to satisfy the boundary conditions. So this will work for any energy whatsoever, but only for specific energies do you meet the condition that the wave function vanishes at the edges of the well, so that an integer number of half wavelengths has to fit inside the well, and so that corresponds to specific energies. You get the quantization and all that good stuff. The main thing we want here is to realize that you'll get sinusoidal-ish solutions when the classical kinetic energy is positive. So I'll riff on that in a moment, but also let you catch up if you have not yet, and entertain any questions that you might have at this point. Can I erase this piece? This piece? Okay. If I rearrange the Schrodinger equation, I got this right. I could make this minus h bar squared times d squared psi dx squared is e minus u psi, and then multiply through by 2m over h bar squared. So here's another way to write the Schrodinger equation, right? If e minus u is greater than 0, then d squared sine dx squared and psi have opposite signs. Right? If E minus U is greater than 0, if the energy is greater than the potential energy, then this stuff that multiplies psi is negative, right? So therefore, the second derivative of psi and psi itself have opposite signs. Classically, what does E minus U represent? What does the total energy minus the potential energy represent classically? That's the kinetic energy, right? That's the kinetic energy. So in a region where classically K is greater than 0, that's the condition that d squared psi dx squared and psi have opposite signs. If E minus U equals K, the classical kinetic energy is constant, then psi will be what we had before, some combination A sine kx plus B cosine kx, or I could also use complex exponential e to the I kx and e to the minus I kx, but I'll keep it real here. Where K squared is, instead of 2me over h bar squared, it's 2m e minus u over h bar squared. In other words, it's just proportional to the classical kinetic energy. So psi is a sinusoidal function with constant wavelength. Right? Little k, right, is constant because E minus U is constant for all values of x over some region. Then psi would be a sinusoidal function, A sine kx plus B cosine kx, with constant wavelength. What would the wavelength be in terms of k? How are k and lambda related to one another? Trying to jog y'all's memories. You want to have it where you just know this stuff. Jog your memory here. How are k and lambda related for sinusoids? Yes?
Lambda is h bar k over c.
You're getting too complicated here. I'm just thinking, even if I've just got sound waves or waves on a rope or something like that, I'm looking for the relation between the wavelength and the wave number. K is the wave number, lambda is the wavelength. How are lambda and k related to one another? If I've got like sine kx or cosine kx, is it not true that sine kx will be the same thing as sine k x plus lambda? Because if I shift x by one wavelength, I've repeated my sinusoid again, right? Sinusoids repeat after one wavelength. So if I add lambda to x, I'm back at the same value of the sine function. So this is sine of kx plus k lambda. But if you've gone through one wavelength, by how many radians has the argument of your sinusoid changed when you've gone through one wavelength? How many radians in one wavelength? Not pi. 2 pi, right? Because there's 2 pi radians in a wavelength, right? You're going for 2 pi radians in one wavelength because that's one full cycle is 2 pi radians. So yeah, exactly. So this is sine of kx plus 2 pi. You've advanced 2 pi radians if you've gone through one wavelength. Therefore, k lambda is equal to 2 pi, and so lambda is 2 pi over k. And also k is 2 pi over lambda. So you want to just be able to do that, right? That shows up all the time. K is 2 pi over lambda, lambda is 2 pi over k, so lambda is 2 pi over k here. Tell me the kinetic energy. I'll multiply it by 2m over h bar squared, and that's the square of the wave number. And then if you want to know the wavelength of the wave function, well, that's just 2 pi over k. So higher energies, shorter wavelengths or longer wavelengths? Shorter, yeah. If the energy is higher, you say k bigger, which means lambda shorter. Shorter wavelengths, higher energies. Matter waves, just like photons, shorter wavelengths are higher energies. Okay? Is this jogging some memory? Is it ringing some bells in the recesses of your brains? Good, this is what we want. Okay. So if I had some region where the potential energy were constant, right here the potential energy is varying with position, but what if I had a well that looked something like this? Here's a potential well. I'm just going to get V as a function of x. Okay. Here's this incoming particle, certain energy, and I want to try to write something that will look like what the wave function looks like for that particle. Then if this is our curve of V as a function of x, then I better be consistent. U as a function of x, then k equals E minus U is absolutely constant in that region right there. And so the wave function will just look like a sinusoid with a constant wavelength there. What happens over here? Is the kinetic energy constant in this region? Yeah, because the potential energy is constant as well. The kinetic energy is just bigger here than it is here. So the wave function here, it'll still be a sinusoid with a constant wavelength, but that wavelength will be longer or shorter than the wavelength here? Shorter, yeah, because it's got more kinetic energy. The higher the kinetic energy, the shorter the wavelength. And I'd have to match up psi and its derivative at this boundary right here in order to pick solutions that actually work. I'm certainly not going to do that, but qualitatively that's the sort of thing that you'd want to do. So if I kind of sketch, very rough sketch of psi for this system, I do something like this. And I'm not claiming this is an accurate sketch at all. I'm not trying to be too careful here, but I'm doing it because I'm going to do something similar over there. So in this region, psi has some wavelength. Let's say it's something like, I don't know. Psi is looking something like that. In this region here, the wavelength got shorter, and so you get something like that. So the wavelength would have switched in between those. But psi is trig everywhere. It's a trigonometric function everywhere. It's a sinusoidal function everywhere there. What questions do you have? What if I had something like this? Make it kind of like this. There's u of x. And here is E. If this is a classical particle, can it make it to the origin? If it's coming in from the right, can it make it to the origin? No, why not? What happens right here? So here, that's the kinetic energy all along these locations. So it's going to come in with constant kinetic energy, E minus U is staying constant. What happens here? What would be the kinetic energy if it were, say, at this value of x? What would the kinetic energy kind of supposedly be if it had this value of x? Not even 0. It would be negative, right? Because the kinetic energy is E minus U in this region. In this region, E minus U is less than 0. So this region along the x-axis is classically forbidden. Since k less than 0 is impossible. 1/2 mv squared being less than 0 ain't a thing. You can't have an imaginary velocity. The velocity is a real number. So this region is classically forbidden. The particle could never get past this point. It would bounce backwards at that point. It's hit a wall, so to speak. And so it would just bounce backwards and head back out. But let's look at the quantum version of this. Again, remember that d squared psi dx squared is equal to minus 2m over h bar squared e minus u psi. If E minus U is less than 0, then kappa squared, we'll call it kappa instead of k to indicate the change that has happened here, kappa squared equals minus 2m E minus U over h bar squared. It's greater than 0, right? If E minus U is negative, if the classical kinetic energy is negative, minus 2m over h bar squared times that is a positive number. So we call that positive number kappa squared. D squared psi dx squared, and psi have the same sign. Have the same sign now. If one's positive, the other's positive. If one's negative, the other's negative. So, can you look at that differential equation and tell me, it's a second order differential equation, so it has linear and all that, so it has two linearly independent solutions. Every solution is a linear combination of those two linearly independent solutions. So when it was minus k squared psi, the two Li linearly independent solutions were sine kx and cosine kx. Or if you use exponentials, e to the plus I kx and e to the minus I kx. What happens in this case? What are the two linearly independent solutions of d squared psi dx squared is plus kappa squared psi? Instead of trig functions, we get what kind of functions instead? You're close. Not logarithmic, but flip that around. What's that?
Exponential.
Exponential. Exponential. Exponential functions are the solutions of this. So in particular, psi will be a linear combination of, you said exponentials, it would be e to what power? What would work? I need two derivatives to get me the same function back, times kappa squared. So what would work? If you differentiate e to the ax, what do you get? A e to the ax. And so if you take two derivatives of e to the ax, you'll get a times e to the ax, right? And so if you differentiate e to the ax, you get a squared times what you started with. Aha! In other words, a e to the kappa x, if I take two derivatives of that, the first derivative will give me kappa a e to the kappa x, the second derivative will be kappa squared a e to the kappa x. It worked. What's the other one? E to the kappa x works. What else works? E to the minus kappa x, right? Because two derivatives are going to get you back to plus kappa squared. Be e to the minus kappa x. Because then d psi dx is equal to kappa a e to the kappa x minus kappa b e to the minus kappa x. But then when I take that next derivative, take that second derivative, I'll get kappa squared a e to the kappa x. I can't write this low. And then minus kappa times minus kappa is plus kappa squared b e to the kappa x. But that's all kappa squared times a e to the kappa x plus b e to the minus kappa x. But that's what you started with. So in a region where the classical kinetic energy is negative, if it were constant, at least the quantity were constant, you get an exponential wave function instead of a sinusoidal wave function. This is key to tunneling. In other words, classically, the particle can't be here at all. But quantum mechanically, you just switch to an exponential wave function. And in general, it will be decaying. The probability will get smaller and smaller as you go, but it doesn't reach zero. And this is like the key to tunneling. You can find a particle in a region where classically that could never go, because the wave function still keeps going. The wave function does extend into that region. That's the key to the idea of tunneling here. What questions do you have? Does that make sense? So in other words, if I were like for sketching this one right here, the idea would be, if down here I'm kind of like going to sketch roughly side, then out here, it's a trig function because the classical kinetic energy is positive. Second derivative has the opposite sign of psi itself. In here, it's an exponential function. Now, it's going to, in general, be a combination of a growing exponential and a decaying exponential. This must be the minus capex there. There's a decaying exponential and a growing exponential. And boundary conditions and normalization will decide what the A and the B would be here. You'd have to match them up with the coefficients of the trig function on the outside. Qualitatively, you'll see something like, aha, the wave function starts to exponentially decay as you go into that region. And psi and its derivative, the exponential wave function in here and its first derivative would have to match the trigonometric wave function and its first derivative here. There's the boundary conditions where the potential jumps, you have to match the psi and its derivative have to be continuous everywhere is what it comes down to. Those are the boundary conditions on the wave function. Oh, and now back in here again, what kind of wave function do we have? If the particle were over here, classically, would that work? Could the particle be here classically? Sure, its energy is, its kinetic energy is positive here. So the particle could be here. So what will its wave function look like quantum mechanically? It'll be shorter wavelengths, but sinusoidal, right? So in here we get something like wee. And this exponential decay means that by the time we get over here, the amplitude has become small, but not zero. So there's a chance you'll find the particle here. Tunneling! Ta-da! There's a chance you'll find the particle here. Because the wave function is small but not zero there, it has made it through the barrier, so to speak. Now, it's probabilities. This is quantum probabilities, but in other words, you just might find it there when you open the box and look. You're more likely to find it over here. It's more likely that you'll have found it reflected, but it just might be inside that box, be inside here when you make your measurement, so to speak. Now, so I should like decorate some more. Psi exponentially decays. As we cross this region. It's still, let's see, it's tricky again. Tricky is my way of saying it's, getting tricky with it because it's sine and cosine over here, right? It's tricky again here since k is greater than 0, but the amplitude is small, but not 0. You might just find it here. Could I make my writing any sloppier? I could, but I'll try not to. You might just. Okay, you just might find it here, but I might just. You might just find it here. I guess that works too. I don't know. Anyway, you might just find it here. Tunneling. Tunneling, it might make it in. might just get over a barrier that it could not get over classically. We've tunneled in. Happiness. We'll dress it up after the break. We'll say, okay, the kinetic energy is changing here. What that means is essentially it's still trigonometric, but the wavelength is getting longer and longer as you get towards the classical turning point. Then it exponentially decays, and then it makes it into the well, and there's a little chance that the particles got through the barrier and fused. So quantum mechanics makes fusion possible at lower temperatures than you would expect classically, because there's some chance in any encounter that the two particles will tunnel through the barrier and feel the strong nuclear force and fuse with one another. Break time. Go, make music. All right, let's do this. What do you think would happen if we made this barrier narrower? Would that increase the chance of tunneling past it or decrease the chance of tunneling past it if you made the barrier narrower? Sorry, so barrier narrower.
Increase the chance.
It would increase the chance, yeah. It would have more chance of tunneling if the barrier were narrower. Intuitively, it doesn't have to penetrate as big a barrier. It seems like it ought to have a better chance of getting past it. If you want to look at it more mathematically, if I just think of it in terms of, okay, if it's not applied, that barrier, then the region over which the exponential decay is happening is narrower. It doesn't drop as far. And so the amplitude on the other side is larger as a result of that. So in other words, it's like, here we go again with all this business here. So let's say it's like coming in here. If it's only exponentially decaying from here to here, instead of all the way over to here, it doesn't fall as far on the way. And so as a result of that, you'll get a bigger amplitude inside the well as a result. And so it's got a bigger chance of having made it inside, so to speak. The narrower the barrier, the greater the chance of tunneling. Since slide decays for a shorter distance. Inside the barrier. That'll show up in a minute when we talk about quantum tunneling for our nuclei, because, oh, the higher the energy, here I had, a constant height barrier over here, but when you got the Coulomb barrier, the greater the particle's energy, the less the distance that it has to tunnel through the Coulomb barrier, and so there's a greater chance of tunneling when the energy is higher, because it doesn't have to tunnel as far as it were. It's closer to having made it over the barrier in the first place. U of x, and this is supposed to be the particle's energy. Questions? And I will also add that I've been treating this as a time-independent problem. I'm just drawing a wave function. And if you think about it, really, a more realistic description is particles moving towards one another, right? There's time dependence here. And you can show that you get essentially the same results. And so you can get away with solving the time-independent Schrödinger equation for all x and matching boundary conditions and interpreting the amplitudes as being proportional to the probability of finding the particle to have tunneled through the barrier. But if what more realistic, you would have a wave packet coming in, some region of significant probability where there's a sinusoidal oscillation within the packet and it goes to zero on either side of it, representing a kind of a wave pulse. The particle comes in, and that wave packet comes in, and it hits the barrier, and partly reflects. You get a wave pulse of reduced amplitude traveling in the other direction, decreases in amplitude, and actually continues inside. You get a partially transmitted wave pulse. And that's how you interpret it in terms of, well, you might find the partially transmitted wave pulse, you find the particle there. More likely, in many situations, you'll find the particle out here somewhere having reflected from the barrier. So it's really a time-dependent problem, but we can get away with this time-independent approach where we just sketch the wave function as though it was a time-independent Schrödinger equation problem that we're trying to solve here. Okay, what questions do you have? I don't remember if I started to. I think I did.
It's blinking.
Did I not?
It's blinking, so I assume you did.
No, I didn't. Oh, okay. No, it is. Yeah, oh, it is. Okay, yeah. Okay, cool. Okay. I couldn't remember. Okay, good. All right. So, let's then kind of sketch psi for our situation here. And so in my notes, I have it drawn something like this. Again, this is pretty qualitative. Is, okay, here's psi. So out here, is the wavelength becoming longer or shorter? So out here is the kinetic energy positive or negative, classically. Positive, right? Because here's the kinetic energy, the difference between E and U. So it's positive kinetic energy. Bigger and bigger the further we get away. So what's happening to the wavelength? Shorter and shorter, right? So in this region where the particles classically allow past our classical, we get something like a wave function that is sinusoidal, and the wavelength is getting shorter and shorter because the classical kinetic energy is getting larger and larger. So something like that. It wouldn't really have the same amplitude. I'm not trying to worry about this. The amplitude would be changing too. I'm just being pretty qualitative here. Okay. Between here and here along the x-axis, what's significant about this region along the x-axis between there and there?
It's going to be exponential instead of...
That's where it'll be exponential. That's where it's the classically forbidden region because the kinetic energy would be negative there. U is bigger than E. So in here we've got the classically forbidden region. Exponential decay. So here's the wave function decaying. Oh. How about over here? Is the particle allowed here if it makes it in there? Classically? Sure. Quantum it says it can be here too, but classically it would say you can't be here. Classically, oh yeah, you can be here. If I put it there in the first place, classically it could be there because it's got a positive kinetic energy. Wavelength in here compare it to the wavelength way over there somewhere. Hint, remember that the binding energy is negative, so it's actually got energy of less than 0 inside the well. So here's the energy, here's the kinetic energy. The potential energy is negative inside the well there. There's the kinetic energy inside the well. Is it moving faster inside or outside the nucleus, in other words? Faster inside or out, well, once they're binding one another, right? Or once they're about to, I don't think about the details, right? Once they bound, it's a different problem. But just thinking of it as two particles approaching one another, blah, blah, blah. What would you say about the kinetic energy here versus anywhere outside? Bigger or smaller? What does this mean?
Smaller.
Bigger?
It's bigger. It's bigger because this is 0 right there from the energy. This is actually negative, right? So the kinetic energy, this is supposed to be K. The kinetic energy is the difference between E and U. U is less than 0 out here. The Coulomb energy goes to 0 far away, but the nuclear binding energy is negative, so you've got a bigger kinetic energy inside here than you do outside the well. The difference between E and U is bigger because U is actually less than 0 inside there. Are you buying what I'm selling? No. Why are you? What's okay?
I wish I could disappear. I did not understand.
Okay, but don't disappear. What you do is you say, no, I still don't get it. Let's talk about this some more. I'm guessing you're not alone. Okay? This is the potential energy, the Coulomb potential energy, right? Go ahead.
It's U is okay.
Yeah, U is well, the whole thing is U, but out here we're beyond the range of the strong nuclear force. So out here it's the Coulomb potential energy, which would be charge 1, charge 2 over 4 pi epsilon naught r. And so that goes to 0 at infinitely far away, and it's positive everywhere else, okay? But the nuclear binding produces negative potential energy, right? The Coulomb repulsion produces positive potential energy, but the nuclear binding produces negative potential energy. So the potential energy is negative inside the well, so to speak. It's less than 0. And so the maximum kinetic energy outside is energy minus 0, because 0 is the potential energy very far away. Inside, it's the energy minus a negative number, because the potential energy is negative inside here. Energy minus a negative number is bigger than energy minus 0. So the kinetic energy is bigger in here than it is anywhere else. So what does that say about the wavelength? The largest kinetic energy will have the shortest or longest wavelengths? Shortest, yeah. So the wavelength in here is shorter than it is in the asymptotic limit way out there. So I'm going to sketch this with a nice short wavelength in here. And it's kind of I'll get sloppy, whatever. Lots of wiggles in there, okay? Maybe we'll find it in there. In other words, maybe it will tunnel through the barrier. It has a non-zero chance of having tunneled through the Coulomb barrier. Psi is not 0 inside the nuclear binding well, so to speak. The nuclei might fuse by tunneling. They just might manage to fuse by tunneling. higher E. Compared to the first one I drew there. Higher E says what about the distance over which the exponential decay would be occurring? It has narrow. It is narrow. Higher E means region through which they must tunnel is narrower. Less decay, higher probability of tunneling. So this means, if you think about it, the nuclear reaction rate ought to increase with temperature, because the higher the temperature, the faster particles are moving, the easier it is for them to tunnel and fuse. Nuclear reaction rate increases with temperature. Since higher T implies higher typical E for the nuclei. And in fact, the nuclear reaction rate is very, as we'll see, very strongly dependent on temperature, which we can understand in terms of, well, if you've got a region where you're exponentially decaying, it makes a huge difference if that region is just a little bit narrower, essentially, because exponential decay very fast, so to speak. Yes?
So if the particle actually tunnels through, does it mean or imply that it's going to fuse, or?
Yeah, if it tunnels through, they will feel the nuclear binding force and they fuse, essentially. Yeah. So, but it's quantum mechanics, and so in other words, it's that whole weirdness, right, and nobody really understands this fully, but in other words, the idea would be, you can imagine, you send these two nuclei towards one another, and as long as you don't look in the box, you could calculate the probability that you will find that they did tunnel through the barrier and fuse, and a probability that they did not tunnel through the barrier and fuse. And when you make the measurement is when they make up their mind, so to speak. But that's strange, because in the real sun, it's not like people are making measurements all the time, right? So nobody fully understands the quantum measurement problem. But at least, you know, our raw material here is we would calculate the tunneling probability. And then we'd be like, okay, this is weird, but then if we want the tunneling, if we want the nuclear reaction rate, we'd say, well, there's so many encounters per second, and the fraction of them implied by our calculation of the percent probability of tunneling times the number of interactions would, the number of close encounters would be the number of actual fusions that we get, something like that. And there's a disconnect between that but nobody looked in the box, but still, that's what you would do, essentially. So, yeah. Other questions? Yes?
What physically equates to like looking in the box? Like what forces it to be one?
Nobody, well, I don't have a good answer for that. I don't. Nobody, if you can figure out the quantum measurement problem, you will be super famous because, you know, we say the words, right? In other words, we say, oh, okay, in the Cohen-Haber interpretation, which is really consistent, but at least we can say, okay, well, the wave function gives us probabilities, and then when you make a measurement, it collapses the wave function, and one of the possibilities becomes reality. Okay, you make a measurement. What does that mean?
why don't you just make a measurement? No, but seriously, what is a measurement? You just make a measurement. Nobody knows. We don't know exactly how to define measurement. At least I sure don't. As far as I know, right, nobody has come up with an ironclad definition of what is a measurement and why does it make the wave function collapse? Or maybe it's many worlds and it doesn't collapse. It's just the universe is splitting into branches. Oh, stop it. I hate that. But it could be true, but stop it. But anyway. Yeah, yeah. I wish I had a better answer for you. Other questions? Here in Philosophy 311. Okay, so we spent a long time being all tunneling here. Probably worth it because I feel like you maybe understand the idea of quantum tunneling better than you did before. So that's fine, that's good. So now let's try to be more quantitative here. It'll require, we will wave some chicken feet, but that's okay. There will be the occasional, take my word for it. In particular, right here, let's wave some chicken feet. A careful treatment was, almost looking at me like, what are you doing, Dr. Herman? I'm waving my hands, but I can't draw hands, so I draw chicken feet instead. So I'm waving the chicken feet, saying, take my word for it. We'll just accept this without going into the details. Are you okay with that? It's like, sure, okay. A careful treatment shows that the particles must approach to within a de Broglie wavelength, whatever the hell it is, de Broglie wavelength, I'll just say it that way, in order for there to be a significant probability of tunneling, right? If they don't get close enough to one another, yeah, there's always some probability of tunneling, but if the energy is low enough, it'd be like, okay, you calculate that that tunneling would happen in more than the lifetime of the universe, right? So in other words, at too low a temperatures, yes, in principle, even at room temperature, two hydrogen protons could fuse with one another because they might tunnel through the barrier. There's never a zero chance of tunneling through the barrier. But on the other hand, the calculated probability is such that them bumping together constantly for the lifetime of the universe would still have a significant probability of tunneling. It ain't happening. So significant probability of tunneling means like in a reasonable amount of time such that it actually, do something useful in terms of powering a star. So a careful treatment shows that the particles must approach to within about a de Broglie wavelength of one another. For there to be a significant probability of tunneling. Or in other words, that the classical approach distance should be less than the de Broglie wavelength for the momentum involved. Does anybody remember what's the de Broglie wavelength? with in terms of the momentum and Planck's constant. Lambda is h over p, Planck's constant over the momentum. That's the de Broglie wavelength. Higher momentum means shorter wavelength, right? That should make sense. So lambda is h over p, so R classical should be less than h over p, that's the de Broglie wavelength. Or in other words, R classical is less than h over, and if we assume that they're not moving relativistically, h over the square root of 2 times the reduced mass times e. Where did I get that from? Why is p the square root of 2 mu m e? What's the kinetic energy? So, well, E here is the faraway kinetic energy. Is there energy of interaction? It's the faraway kinetic energy, right? So, E is what in terms of the momentum? Kinetic energy is what in terms of momentum? What's it in terms of V? If I have a particle of mass mu sub m, what's its kinetic energy? Mu v squared, right? What about in terms of its momentum? What is kinetic energy in terms of momentum? If you want that to be, it's even better to think of it in terms of momentum than speed. No, that's angular momentum.
Momentum squared over 2m.
Yeah, p squared over 2m, right, is kinetic energy. So E is p squared over 2, since it's reduced mass, 2 mu m, right? And so therefore, that's why p squared is 2 mu e, or p itself is root 2 mu e. When I say mu here, it's understood as mu sub m, because okay. So here's our condition. But we have our expression for R classical. That was Z1, Z2, E squared over 4 pi epsilon naught E, as we said that at closest approach, their potential energy becomes equal to the kinetic energy that they had before, the kinetic energy E, from far away, which is their energy everywhere, and it's all potential at closest approach. So E at closest approach is Z1, Z2, E squared over 4 pi epsilon naught R. It's all potential energy at that point. Flip it around, solve for our classical. Right, by that, we'll do this. Okay? So therefore, we can say that H bar, sorry, H, not H bar, H over the square root of 2 mu E should be less than, should be greater than, I'm going to flip it around here, should be greater than Z1, Z2, E squared over 4 pi epsilon naught E, because I flipped the direction, right? In other words, R classical is less than H over square root 2 mu E, which means H over square root 2 mu E is greater than R classical, which is that expression right there. So now let's multiply through by E, and E over the square root of E is the square root of E. So this turns into square root of E over 2 mu is greater than Z1, Z2, E squared over 4 pi epsilon naught h. So this says, solving for E, square both sides, and move the 2 mu to the other side. E should be greater than mu z1 squared, z2 squared, e to the 4th power divided by 8 pi squared epsilon naught squared h squared. For fusion, when quantum tunneling is taken into account. And of course, now we put in some numbers after setting. We'll say that E is 3/2 k T sub quantum. So we'll think of that as, in other words, the typical thermal energy, 3/2 k T needed. So setting, turning this into a temperature using E equals 3/2 k T quantum. QU. So in other words, we're thinking of, okay, this tells us what energy the particles need to have, what temperature do we need for them to have that much energy typically. And again, 3/2 kT is the good estimate of what a typical particle energy is at a given temperature. We have for the minimum fusion temperature, T quantum equals mu sub m z1 squared z2 squared e to the 4th power over 12 pi squared epsilon naught squared h squared k. And really this is getting kind of fussy here because this is really just kind of an estimate, and so it's a little bit silly to worry about the 12, for example, but that's all right. And if we plug in the numbers for the proton-proton interaction, 2 protons gives us, look at that, about 10 million Kelvin. Is that good agreement with the sun's central temperature? It is. The sun's central temperature is like 16 million Kelvin. And furthermore, detailed calculations show that 10 million Kelvin, in fact, is about the temperature of the proton-proton chain igniting. In good agreement with the sun's core temperature. And so we make our overall conclusion yay, tunneling! Quantum tunneling lets us live to talk about quantum tunneling. There's something beautiful about that. You look like you're not happy. Yes?
Just what's D sub QU?
Oh, quantum. In other words, this is like T sub Cl is the classical temperature needed for fusion, and that was like 1,000 times larger than this. T sub QE, we're calling like the temperature for fusion if we take quantum mechanics into account. So TQU just means that, T quantum, if you will. It's not a quantum, it's not literally a quantum mechanics temperature, it's our estimate of what temperature is needed for fusion when we take into account quantum tunneling, TQU for short.
Why is there such a big difference?
Because of the fact of the tunneling business. In other words, right, so classically, I need to have the energy up there. Quantum mechanically, I can be down here somewhere because I can tunnel through the barrier. And so that's what it comes down to, is that for 1,000 times lower than the classical temperature needed to overcome the barrier, you still get a good enough probability of barrier penetration of tunneling that fusion is viable. And so, can I, in a nutshell, say why it's a factor of 1,000 exactly? Not exactly, but why is it 1,000 and not 100 or 10 or 7 or whatever? I can't do that off the top of my head. But fundamentally, it's because quantum tunneling allows you to have a lower energy and still fuse, because you don't have to get within a Fermi of one another. Classically, to fuse, they get quite a bit further away from that, but there's a little chance because of quantum uncertainty, right? Because particles don't have definite locations, right? Classically, we're thinking of having definite locations, and if those definite locations are more than a Fermi apart, they can't feel the strong nuclear force. Quantum mechanics particles are fuzzy, and so it's like, yeah, okay, here's the centers of the fuzzballs, but those fuzzballs are overlapping in the region where if you found the particles there, the strong nuclear force would attract them together, and so it'd be like, whoop, whoops, we found them there, and they fuse, so to speak. Yeah. Right? There's some chance that they do fuse, because there's some chance that they kind of do find themselves that close to one another. So, hence, hooray, we can live and talk about quantum tunneling because of quantum tunneling, and many other things. Yeah, that's the idea. Okay. What other questions does anybody have? Okay. Let's see. So, last thing I want to talk about in this chapter, which will take us another class worth, is reaction rates, nuclear reaction rates. Talking about how fast the nuclear reactions go. And so we'll learn some nuclear physics-y, particle physics-y things here. We've mentioned cross sections before. We're going to use them again. Concepts that are important for people that do particle physics and nuclear physics. So we'll get a taste of them here. And for that matter, so did any of you ever do in chemistry class a discussion of reaction rates in terms of concentrations and stuff like that? I did when I was a freshman in college, and it made no sense whatsoever to me. I'm like, this is just hocus pocus. It felt like you're just making this crap up. And so if that's you, if it made sense to you, great. It'll make sense to you again when we do it in this nuclear physics context. If it didn't make sense to you, maybe I can help it make sense to you because it's the same stuff. The same kind of considerations for talking about reaction rates in terms of concentrations for chemicals, for atoms interacting chemically, also apply to nuclei fusing with one another. So that's the machinery we're developing here to discuss reaction rates. Part of the problem was, I haven't seen the book in a long time, but my chemistry book, my recollection, maybe this was my subjective feeling because I was not understanding it. I felt like you were just writing equations down and saying, here's the equation, take a word for it, and that just does not work for me. We need to know why equations are what they are, not just what the equations are. I think it's why engineering is not for me, because I mean, it's overdoing it. It's not quite like that, but engineers are much more willing to like, here's the equations, let's use them. And I was like, no, where did that come from? So I don't know about you. Maybe you're like, nah, just tell me the equations. But in any case, reaction rates. So epsilon, right, which remember is the energy generated per unit mass per unit time. So what would the SI units of that be? What's the SI unit of energy? And the unit of time?
Seconds,
And the unit of mass?
kilograms.
Right, so this would be joules per second per kilogram, but what's a joule per second? What is a joule per second called? A watt, right? So this would be watts per kilogram is the units of this. The number of watts per kilogram that the nuclear reactor is generating. This will be the sum of the available energy generated per reaction we say available energy because often we don't consider, for example, we don't count neutrinos because they don't interact with anything else, and so they just stream right out of the sun. And so sometimes we don't include neutrinos in epsilon, although we can. Times the number of reactions per cubic meter per second. So how much energy comes out of each reaction times the number of reactions per cubic meter per second times, since we want to have the units be watts per kilogram and not watts per cubic meter, times the number of cubic meters per kilogram. So the number of cubic meters per kilogram is the reciprocal of the number of kilograms per cubic meter, and the number of kilograms per cubic meter is the what? What do you call kilograms per cubic meter? Starts with a D. Density, yes. Density. What symbol do we use for density? Rho. Yeah. So that term right there is rho inverse. It's the inverse of the density right there. Okay, and now we're going to make a chain of reasoning about our chains of reactions here. And this is the part that I never understood when I was a poor first-year chemistry student about when we were talking about reactions and stuff like that. But I understand it now. And again, I hope you understand it as we explain it here. And if you don't understand, well, you're going to be bold and ask me questions about it. So, this term right here, so right here, the second term on the right, this is the key point to understand. The second term on the right is the same for all the reactions in a series such as the proton-proton chain if the reactions proceed at equilibrium. It's the same for all the reactions in a series such as the proton-proton chain if the reactions proceed at equilibrium. since otherwise the concentrations of some intermediate reactants will be building up or diminishing. Capitalize concentrations. And by that I mean like the number, it's basically the number density, the number per cubic meter of those things. The concentrations, the number density, the number per cubic meter of some intermediate reactants and in equilibrium, the concentrations are supposed to be holding steady. The initial reactants, the final products, well, those are changing because you're using up hydrogen to form helium, for example. So we don't expect the number of protons in the sun's core to hold constant. Even if the reactions are in equilibrium, we don't expect the amount of helium-4 to hold constant. It's being built up. But the intermediate stuff, if it's in equilibrium, those thingies should keep constant concentrations. So of some intermediate reactants will be building up or diminishing. So why is that? So remember, that there's the second step of the proton-proton chain. A proton fuses with a deuterium nucleus to form a helium-3. So here's an intermediate reactant. Here's an intermediate reactant. And then helium-3 fuses to form helium-4. Let's suppose, and we'll show that this can't be, suppose the concentrations of deuterium and helium-3 were equal to one another. There were equal amounts of deuterium and helium-3. So I'll say this now to put it into your heads, and we'll say it again next time, because we don't have time to finish this right now. But just to like complete this idea here in words, and then we'll write this all out next time. So, which of these reactions is easier? The deuterium fusing with a proton, or the helium-3 fusing with another helium-3? And we had it in terms of how long a deuterium lasts before this happens versus how long a helium-3 lasts before this happens. Which one survives longer, a deuterium or a helium-3 before it undergoes the next reaction? Survives longer? Turn it around. Yeah, it's the other way around. Yeah, the deuterium is very reactive. So deuterium almost instantly gets turned into helium-3. But helium-3, a newly minted helium-3 nucleus lasts about 400,000 years on average before it fuses with another helium-3. So suppose that there were comparable concentrations of deuterium and helium-3, right? What's going to happen? Could that remain the case? No, because the deuterium is going to be very rapidly turned into helium-3 because that's easy to do. And so if you somehow, rigged it so that there was equal amounts of deuterium and helium-3 around, that's not going to last for long because the deuterium is going to quickly turn into helium-3. But what eventually happens is now there is so much helium-3 around and so little deuterium around that the reactions proceed at the same rate. Because even though It's much easier to fuse any individual deuterium than it is to fuse an individual helium-3. There are so few deuterium around and so many helium-3 around that the rates are equal to one another. And so that's the idea with these kind of equilibrium concentrations kind of things, is that the concentrations of things that react easily are much smaller than the concentrations of things that are hard to react, because you need a lot more of the things that have a hard time reacting to have them react at the same rate overall as the things which undergo an easy time of reacting. And so we'll flesh that out next time, but that's the idea here. That's all these intermediate steps have to be happening at the same rate, and it happens because the concentrations are very different. There's a lot more helium-3 in the sun's core than there is deuterium in the sun's core, because those reactions have to be happening at the same rate for everything to be in equilibrium. The end for now. Yes?
Real quick question, the intermediate reactants are the He32 or just?
Yeah, so the deuterium and the helium-3 are intermediate reactants here. Yeah. Stuff that's built along the way to building the final product.